In this section, I want to show you how we can perform rotation on a vector space. In particular, as we already did in projection, we can define this operation as a linear map. In particular, we define rotations as automorphisms. Remember, an automorphism is a linear map that from values vectors in a vector space V returns to us vectors on the same vector space. In particular, we will consider in the next slides V as a non-Euclidean vector space. So R of theta rotates, is an automorphism that rotates vectors by an angle theta with respect to one axis that passes through the origin. So we select the axis, we choose the angle, and then this linear map rotates every vector we input to the function. In particular, since R of theta is a linear map, then we can associate to it a transformation matrix, R of theta. This transformation matrix is said to be a rotation matrix. In here we will see a particular case of a 2D plane, and we try to define and determine the rotation matrix. Of course, the rotation matrix depends on the basis we choose, and here we will use the usual basis, the canonical one. So from the canonical basis, we rotate them by an angle theta. To express this operation, we can of course use the rotation matrix, and then we want to determine the result. Well, the result can be determined considering this graph. So here we have rotate vectors. So E1 is of course parallel to the x-axis. Here we have. So rotating it by theta means that the x value will be cosine of theta, and the epsilon value, or epsilon coordinate, will be sine of that angle. If so, the rotation of E1 by an angle theta results in a vector with components cosine of theta, sine of theta. In the same way, we can determine the rotation for E2. Here you can see the same rotation is performed with an angle theta, and we can see that the x coordinate would be minus sine of theta, while the y component would be cosine of theta. And here we report the result. Thanks to these two operations, and knowing that the canonical these two vectors are the canonical basis, then we can write the rotation matrix, where every column of this matrix is the rotated angle, rotated canonical basis by an angle theta. We can prove, but we will not do, that the two vectors, the rotated canonical basis, are orthonormal bases. In particular, I left to you to prove that the rotation of these vectors is still a basis, but I want to show you why we talk about orthonormal basis. So I want to justify why this basis, these two vectors, are orthogonal and normal. First of all, let's take the dot product between the two vectors. If the two vectors are orthogonal, the result of this operation must be equal to 0. And that's it. In fact, we obtain cosine of theta times minus sine of theta plus sine of theta times cosine of theta. This is, of course, equal to 0. So we have just demonstrated that these two vectors are perpendicular, are orthogonal. They are also normal, because if we take the dot product with which is if we take the length of these vectors, we are just computing the Euclidean norm, and we know that a property holds for sine and cosine, and that's that the square of the cosine plus the square of the sine is equal to 1. So the square root of 1 is still 1, and then the norm of these vectors are equal to 0. So we didn't prove that these two vectors are a basis, but given this information, we can say that these two are an orthonormal basis. This is pretty important, a pretty important consideration, because let's get back to a generic square matrix, and we say that this matrix is an orthogonal matrix if and only if the columns are orthogonal, like we have seen for rotations. And in particular, we can demonstrate that if the columns are orthogonal, then, or better, orthonormal, then this property holds. So A times the transpose of A equals to the identity matrix, and the same for A transpose times A. But let's see why this property holds if the columns are orthogonal. We take a basis of n vectors. We are in fact on a r times n times n space. So every column here that define the A matrix is a vector. So every column contains the components of each vector in the basis. If we do the multiplication between matrices, we multiply, for example, for getting this element, we multiply this row by this column, and so on. As you can see, we get nothing more than the dot product on a R n times n space. Since the bases are orthonormal, then we get 1 on the diagonal and 0 elsewhere, which is the expression for the identity matrix. In particular, since this property holds, it means that the inverse of the A matrix is equal to the transpose of that matrix, which is a pretty important property, because if we need the inverse matrix, we don't need anymore to obtain it, to compute it with some complex algorithm, but we just need to transpose the original matrix. Also, if the matrices are orthogonal, and let's say we can write a linear mapping using an orthogonal matrix as a transformation matrix, then we can see that this linear map, and thanks to the orthogonal matrix, preserve the vector's length. In fact, considering this this operation, which is the application, the computation of the linear mapping, and let's consider the square of the norm. Of course, the norm to the power of 2 is equal to the dot product. So we can do the dot product. We apply the transpose to this element, which means that it results on X transpose times A transpose. We have to switch the two vectors slash matrices in applying the transpose. Then we know that since the A matrix is orthogonal, this product will result in the identity matrix, and so we get that the norm or the square of the norm of A times X is equal to the square of the norm of X. We have previously demonstrated that we can express rotation using an orthogonal matrix. So we can say that rotation preserves the length of the rotated vectors. Here, in fact, these two vectors are orthonormal. So, applying the rotation to the x, and this vector length is equal to the length of the original vector. But we can say more about rotations, and in fact, we can say that rotation preserves the distance between the rotated vectors. In fact, this property holds even if we consider the x minus y, and we take the difference between the two rotated vectors. In fact, here we can demonstrate, we can prove this property for a generic orthogonal matrix. And in particular, we can show that for an orthogonal matrix, not only the lengths are preserved, but also the angle between the vectors. The computation is very similar to what we did in the previous slide, and it simply holds that the cosine of omega of the transformed vectors is equal to the cosine computed between the original vectors. Again, we can say that the rotation matrix, since it is an orthogonal matrix, preserves the angle between the rotated vectors. So, in this course, we have seen several properties and objects in the vector space. In particular, our task was to determine some geometric properties for the vectors. We defined, for example, the inner product operation, and we've shown that this operation induces norms in which we define the length of the vector, and induces the matrix which we use to measure the distance between two vectors. Also, inner product allows us to define, for example, angles between vectors. In the other section, we've talked about orthogonal projections, and using their projection matrices allow us to project vectors on a vector subspace in a way that the original and the projector vectors are at the minimum distance. Third, we've seen that the rotation of a vector can be done using a rotation linear mapping, and in particular its transformation matrix, the rotation matrix, contains sine and cosine elements. So now, in this course, we have defined several tools to measure distances and vectors. We will use these tools to gain better insights of the reality, and in particular to measure the performance of the machine learning models.